Welcome to our video on quantum numbers. If you're taking chemistry, you've likely encountered these numbers that describe the properties of electrons in atoms. In this video, we'll break down the four quantum numbers: principal, azimuthal, magnetic, and spin, and make them easy to understand. Quantum numbers are essentially address labels for electrons in atoms. Just like you need a complete address to find a specific house, you need all four quantum numbers to identify a specific electron. Let's start with the principal quantum number, n. This number tells us which main energy level or shell the electron occupies. It can take positive integer values starting from 1. These correspond to the k, l, m, and n shells you might have heard of. As the principal quantum number increases, both the energy of the electron and the size of the orbital increase. This means electrons with higher n values are generally farther from the nucleus and have higher energy. Next is the azimuthal quantum number, L, which determines the shape of the orbital. It can take integer values from 0 up to n-1. Each value of L corresponds to a particular subshell, which we label with letters S, P, D, and F. Let's visualize these orbital shapes. The S orbital, L equals 0, is spherical. The P orbital, L equals 1, has a dumbbell shape. The d orbitals, L equals 2, have more complex shapes, often described as clover-like. And f orbitals, L equals 3, have even more complex geometries. Our third quantum number is the magnetic quantum number, m sub L. This tells us about the orientation of an orbital in space. For a given value of L, m sub L can have values from negative L to positive L, including 0. So there are 2L plus 1 possible orientations. Let's see what this means in practice. For s orbitals, where L equals 0, there's only one possible orientation, with m sub L equals 0. For p orbitals, where L equals 1, there are 3 possible orientations: m sub L equals -1, 0, or +1. We call these px, py, and pz orbitals. Finally, we have the spin quantum number, m sub s. This describes the intrinsic spin of the electron. It can only take 2 values, plus 1/2, which we call spin up, and minus 1/2, which we call spin down. Let's put it all together with some examples. In the hydrogen ground state, the electron has quantum numbers n equals 1, L equals 0, m sub L equals 0, and m sub s equals plus 1/2. For a carbon atom, one of the electrons in the 2p orbital might have quantum numbers n equals 2, L equals 1, m sub L equals -1, and m sub s equals -1/2. There are 3 key principles to remember when working with quantum numbers. First, the Pauli exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers. Second, the Aufbau principle tells us that orbitals fill in order of increasing n plus L, and if 2 have the same n plus L, we fill the one with lower n first. Third, Hund's rule says that for degenerate orbitals like p, d, and f, electrons first occupy different orbitals with parallel spins before pairing up. Finally, let's look at a summary table of subshells. This table shows how the quantum numbers relate to each other. For the first shell, where n equals 1, we only have the 1's subshell. For the second shell, where n equals 2, we have the 2's and 2p subshells. And for the third shell, we have 3's, 3p, and 3d subshells, each with their corresponding magnetic quantum number values. And that's our comprehensive look at quantum numbers. The 4 quantum numbers, principal, azimuthal, magnetic, and spin, completely describe an electron state in an atom. Understanding these numbers is crucial for predicting electron configurations and chemical behavior. Thanks for watching, and I hope this made quantum numbers a little easier to understand.